Hello and welcome to this lecture, continuing the introductory remarks, the introductory or basic concepts of analytical mechanics. Basic concepts of analytical mechanics. So in the last lecture we introduced or we studied the following concepts. Of course we revised Cartesian coordinates, and we remarked that Cartesian coordinates is just a special case of the generalized coordinates, and we also emphasized that a special subset of the generalized coordinates are the degrees of freedom, and the straightforward question is why the generalized coordinates are not just the degrees of freedom, because there is something that we introduce to our system which is called the constraints. And we have illustrated the famous formula is that the number of the degrees of freedom n is equal to the number of the generalized coordinates n capital minus, for example, the number of the constraints, which is equal to m small. So on this lecture now we will try to progress more on these introductory concepts. As I have already mentioned, we will introduce the concept of the virtual displacements and the concept of virtual work. So let us go further now. What's meant by the virtual displacement? It's a very interesting topic, or a very interesting concept. In fact, indeed, everybody is. We are all familiar with the displacement, with the concept of a displacement in general. If we have a mass m, then this mass is displaced from one position defined by vector r1 to another position defined by vector r2, and indeed this is the displacement delta r, such that delta r is equal to r2 minus r1. Of course, we are all familiar with the concept of displacement. The position changes from one point to another, so the particle is displaced because the place itself changes. So that's the concept of displacement. So what is a virtual displacement? It's not a real displacement, indeed. It's a virtual one. It's an imaginary displacement. It does not occur in reality. It does not occur in reality. Does not occur in reality. So what's the reason for introducing such strange concept? It does not occur. Does not occur. So how is it useful in fact? Before answering this question, I would like to draw or to point or to list the following properties of a virtual displacement. Indeed, one of its properties is that the virtual displacement does not occur in reality. However, this is not the single property. There are other properties in fact. The first one is that with a single word, it is instantaneous. What is the meaning? A virtual displacement occurs while time is held constant. It's very strange, of course. Indeed, in the first example, when I try to explain the meaning of a displacement, the displacement means the particle is initially at this position and then it moves or is displaced to this position. It will take a finite time to move from this point to this point. However, when we speak about virtual displacement, we imagine that a displacement, which is not real of course, occurred in no time, in zero time. Indeed, this is strange. However, there is nothing strange because we are speaking about a virtual or an imaginary displacement. The second property of a virtual displacement, and by the way, it is always termed by the symbol delta r, is that it is infinitesimal. Infinitesimal. It's very small. It's very small and it's very close to zero. However, it's not a real zero. It's not an exact zero. It's just infinitesimal. And the fact is that the virtual displacement is infinitesimal is very important, because a consequence is that if a virtual displacement occurs, the state or the condition of the system is not changed. This virtual displacement does not change the condition of a system because it is infinitesimal. It's very small. However, it's not a zero. Another important property of the virtual displacement is that it is arbitrary, and it's very important to stress this property. Now, it is arbitrary. It is not zero. It's very small, yes, but it is arbitrary. It can take an infinite, takes, or it is equal to, or can take infinite values. It's very strange, yes. However, or it is very, I know the concept is very strange, but this is the concept itself. You cannot say that it is equal to some very, very small number. You cannot say this. Or you cannot relate it to another variable, for example. No, it's not related to a specific variable. It can just take any value, and you can just say that it is independent on the other parts of the system. So it is just arbitrary. Yes, it's very small, it is infinitesimal, but it is not a zero. It's just arbitrary, so I'll write it here. It's not a zero. The last one, which is related to mechanics, the concept of virtual displacement can be used in either statics or in mechanics. So if you are going to use it in mechanics or in dynamics, for dynamics, you will have to use the following condition. You will have to impose that the virtual displacement obeys the constraints. It does not violate the constraint. So this property is very useful in dynamics, and we will almost stick. We will not move away from this assumption or from this property. Indeed, if this property or if this condition is relaxed, you can even use the virtual displacement to get something useful in statics, but this is like, we don't need to go through this while we are studying dynamics. So this is all regarding virtual displacement. The main question is, how is this thing useful? This is the main question now. Why is this concept useful in any way? That's we are going to answer now. Let us go for next slide. So to know why this is useful, we will write the following principle, which is mainly attributed to the French scientist Lambert. The Lambert's principle. So what is the Lambert's principle? It simply says the following: since for a system, and we will begin with the static problems, we cannot go now to dynamic problems. To understand it fully, let us stick to statics. Indeed, so in the Lambert principle, it begins with the principle of equilibrium. So if a system is under equilibrium, then the summation of the forces, all the forces, and here the summation takes both the external forces and the constraint forces. Both of them the vectorial sum is not just two forces, no, many external forces and many constraint forces, their vectorial sum is equal to 0. So this is the principle of equilibrium, and it's a vectorial equation. Now the Lambert's principle is very close to the equilibrium, but it is written in a scalar equation. Sigma f multiply delta r, well, delta r is a virtual displacement of a system, is also equal to 0. Now this is a 0 vector, however this one is a scalar. And indeed we like scalar more than vectors. That's why this new equation may be useful. But indeed we are faced with a very important question. What's delta r? Yes, we have already explained the conditions for delta r, but how to compute delta r in a real problem and how to get something useful from delta r. So more or less, like, but before going to a solved example, I will try to answer this. Given that r is a function of the degrees of freedom q1 and q2 and so on, and time, the virtual displacement can be computed in the following. The virtual displacement will be equal to partial r by partial q1 delta q1. Now we have a variation or a virtual change in the degrees of freedom plus partial r by partial q2, which is a partial derivative, by the way, delta q2, plus you will not write partial r by partial t. This one is not written. Why? Because if we go back to the last slide, one of the conditions imposed on the virtual displacement is that they are instantaneous. Time is held constant. So delta t is something, we don't deal simply with delta t, so you can say that delta t is equal to 0, exact 0. So that's all. So this is the virtual displacement in terms of the variations or the virtual changes in the degrees of freedom. That's how we will compute the virtual displacement in all the applications in this course in general. So let us take an example, and an example from statics, just because statics is simple than dynamics. So let us try to solve the following static problem. Assume that we have here a hinge. We are having a hinge here, and then for this hinge you are having a rod, and this rod have a weight. It's not a massless rod, it just have a weight, and the weight of the rod acts at its center. And you would like to, or somebody here standing up here, his hand is very long, he's a very long man. That man is holding the rod. So he's holding the rod by applying a vertical force F, which is indeed an external force. So the man applies the force F to hold the rod from getting down, from rotating downwards. So the question is, what's the value of F? And we can try to solve this problem in terms of the following, in terms of the tilt angle theta, and in terms of the length of the rod, L. And we will solve this problem without using statics, but we will solve this problem using the concept of the Lambert principle, using the virtual displacements. So this is just what we are going to write. Delta or sigma f dot delta r will be equal to 0. So this is, by the way, the virtual work. So we will compute the virtual work and equate it to 0. Now, how many forces we have now? We have the red force F. Unfortunately, it's a vectorial equation. The virtual work is a vectorial equation. Indeed, the result is a scalar, but still the left hand side is written in terms of vectors. So we must and we have to write all the forces using vectors. That's why I'm going to introduce now here the following Cartesian coordinates: x horizontal to the right and y vertical upwards. So if we do this, we can write f in this way: 0 horizontal component and the vertical positive component equal to f. And indeed, it will be very easy to write w, which is equal to 0 and negative w. So the question is, where is delta r now? We have the following situation. We have to be very careful now. W acts at the point at this point, and f the way it acts at this point, let us call it Rw. It is the position vector of the point at which the weight acts, and the force F acts at the tip of the rod, of course, at another point. We can call it R what? Rm or whatever. So the virtual work will be equal to F dot delta Rm, and I'm using the colors to illustrate my idea, plus the weight dot delta Rw. This is equal to 0. Once this equation is written, we will going to get F in terms of W, as we are going to see now. So how to get delta Rm and delta Rw? The answer is not so difficult. You need to write or let us begin with Rw, which is equal to L over 2 cosine theta and sine theta. These are the Cartesian coordinates of Rw. And indeed this distance is L over 2 because the weight of the rod acts at its middle, at the middle of the rod. So if this is Rw, indeed you can write Rm, but let us postpone it a little now because we are interested in delta Rw. As we have mentioned, or as we have explained, as I have explained in the last slide, you get the virtual displacement in terms of the variation of the degrees of freedom, deltas. So delta R. So fortunately, in this problem, we have a single degree of freedom, which is theta. Just if you know theta, then the configuration or the condition of this small system is completely determined. So you will get delta Rw in terms of delta theta, which will be equal to partial Rw by partial theta delta theta. So the answer is L over 2 minus sine theta. Of course, we are now making partial differentiation with respect to theta. I'm sorry, I need the eraser, because partial sine theta by partial theta is equal to cosine theta. And please do not forget delta theta. Similarly, you can write easily Rm, which is equal to L cosine theta sine theta, and you can write delta Rm, which is equal to L negative sine theta cosine theta delta theta. Now it is time to return back to the basic principle of virtual work, or in fact we will use this equation. So the first term, which is F dot delta Rm, F dot delta Rm, yes, you will make the dot product between this vector and this vector. Unfortunately, you have here a 0, so this sine theta or negative sine theta does not contribute to the result. You just will have F L cosine theta delta theta. So this is which term? This is the first term. Now let us go to the second term, which is the weight dot delta Rw. You will make a dot product between this one and this one, and also fortunately the x component does not affect the solution, but please don't forget that we have minus w multiply L over 2 cosine theta delta theta. So we will have here a negative w L over 2 cosine theta delta theta, which is all equal to 0 due to the principle of virtual work. So what we have got now, first of all, cosine theta can be omitted because cosine theta is not a 0 unless we are speaking about theta is equal to pi over 2, which is excluded from this solution now. And L is non-zero, is not a 0 also because we are not speaking about a zero length rod. And by the way, we are left with this very interesting result. It is F minus W over 2 delta theta equal to 0. So we have now two suspects, in fact. It's either F minus W over 2, which is equal to 0, or it is delta theta equal to 0. However, we have already excluded the second option. Delta theta can never be equal to 0 because the virtual displacement can never be equal to 0. Yes, delta theta is infinitesimal, but it does not take a specific value, so it is not a 0. So we are just left with the first option, which is F minus W over 2 equal 0, or just F is equal to W over 2. That's the first, so this is the result. The second, and the very important, somebody may have asked here, working with this delta F term, we just took into account the external forces only. Is it correct? Why didn't we take the constraint forces? Do we have here constraint forces? Yes, we have here in this hinge constraint forces. They are stopping this point from translation. Why didn't we take them into account? Because simply if you see the following, if you try to take them into account, you will see that you have here Rx and Ry. Rx and Ry, yes. So what is their value? We are not interested in their value. In the beginning, we were just interested in the value of F. We are not interested in the constraint force. So we did not ask this question. However, we were not even forced to find Rx and Ry, because simply Rx and Ry did not do any virtual work. Rx and Ry acts at the hinge, and the hinge did not move. Indeed, due to the virtual displacement, Rw moved and Rm moved. However, this point, the hinge did not move. Why? Because a very important condition on the virtual displacement is that they do not violate the constraints. They obey the constraints. So since they obey the constraints, the hinge did not move, and consequently the reactions at the hinge did not move. And by the way, this very nice result we will always exist in the virtual work, and you can write here something like a result or something to be happy about, that constraint forces do not contribute to virtual works. Very nice. If you are interested in the constraint force, then one option for you now is returning to the Newtonian mechanics and writing the three equations. In fact, sigma fx of equilibrium and sigma fy and sigma moment at some specific point, and equating the result to 0. And by the way, you will have three unknowns, which is Rx and Ry and F. However, if you are not interested in Rx and Ry, going in this way or in this method will be just a waste of time. So maybe you can appreciate now the strength or the power of the method of virtual work or virtual displacement or the Lambert Principle. So let us move further with one final example. Suppose now we have the following situation. Suppose that we are having here some ceiling or a wall, and we have here the following. We have a pulley, which is a smooth pulley, and from this pulley we are having a weight W hanging, and we are having another pulley here, okay, and we are having the green rope which just goes around this pulley, then goes to around this pulley, and then we are having some person in blue. This is his hand. This person standing here, and he's pulling or applying an external force downwards here to stop the weight from falling. So the question also now, what is the relation between F and W? And the answer of this question will be in terms of the following, will be in terms of this tilt angle, the tilt angle of the rope, which is theta, and in terms of this length, which is equal to which is equal to L capital, which is the distance between the left support and the right pulley. Both pulleys are smooth. So we will repeat our steps now using also the principle of virtual work. So we will deal with 2 points. Let us denote this point by RW, and let us denote this point by RM. And the solution will come from the following. We'll just write F dot delta R, F dot delta RM plus W dot delta RW, which is equal to 0. However, this one will be a little bit difficult due to some more mathematics or mathematical details. So how we will go on now? F here will be equal to 0 and negative F, and W will be equal to 0 and negative W. So what about Rm now? Rm will be equal to the following. We can take here coordinates x and y. So in this case, Rm will be equal to what? We will have a 0 in the x direction, and in the y direction you will have a value equal to what? Equal to d. So it's 0 and minus d. D is a variable. It's not a constant. Variable in terms of the constraint theta. There is some relation between d and theta, as we are going to see later. So what about Rw? Rw will be equal to what? Will be equal to minus L, using, by the way, L is a constant, and minus A, where A is this distance. And let me remind you that A should be a function in theta, and that's what will take some time for you to get. We need now to get the following. We need to get delta Rm, which is equal to partial Rm by partial. In fact, you can imagine that you have a single degree of freedom here, which is d. So it will be partial m by partial d. Sorry. Yes. partial m by partial d. But why to write it partial m by partial d delta d? Or you can write it partial m. Let us go to this way anyway. Where partial m by partial d is equal to 0 and minus 1 delta d. There is no problem at all in going in this direction. And then partial w also, the delta rw can be equal to what? Partial rw by partial a delta a. This is also correct. And as I have already told you, L is a constant. So it's very nice. So its partial derivative will be a 0 and you'll have minus 1 delta A. So the question is now, what is the relation between delta D, delta A, and indeed the single degree of freedom of this system is delta theta. What is the relation now? If we can solve this relation, the answer will be very clear. In fact, the dot product is so easy. You will just write f dot delta Rm. It's very clear that you will have the following from the dot product: the 0 dot multiplied by the 0, 0 multiply 0, you will just have a 0, and minus f minus 1, so you will have f delta d. And also for the same, you will have w delta r, so we'll have w a, w negative w by negative 1, so we'll have w delta a. It's equal to the, that's all. So the key for our problem now is finding the relation between d and a and t. So how to solve this problem now? We'll go to the following. Assume that this length is equal to b, and please remember that this green rope is inextensible, so its length is a constant. So although a and d and b are not constants, however their summation is a constant, so a plus b plus d is equal to a constant. This is very important. This is very important. This is the first one to be used. The second one is the relation between L and B. In fact, B here is the hypotenuse of this right angle triangle. So L is equal to B cosine theta. L is equal to B cosine theta. So what we can do now, so L is a constant, so if you take the partial derivative of this equation with respect to theta, for example, or let us just evaluate the variation of both sides, you will have the following: 0 equal to delta b cosine theta plus or minus b sine theta delta theta. And also for this equation, find the variation. So delta A plus delta D plus delta B will be also a 0. So we have now two equations. This is the first one, and it's relating delta B to delta theta, and this one which is relating delta A, delta D, and delta B. So we have now delta A, delta B, delta theta, delta D. 4 variations. However, we need to find everything in terms of only one variation, which is delta theta. So how to solve this problem? After thinking one more, you can see that B cosine theta is equal to L, but also B sine theta is equal to A. It's very important now. So B sine theta is equal to A. Take the variation for both sides. So delta B sine theta plus b cosine theta delta theta is equal to delta A. So this is the third equation. Now we have three equations for delta B, delta theta, delta A. Three equations for this variation: delta A, delta B, delta theta, delta B. So we can get rid of all the following. We can get rid of delta B and delta A and delta D in terms of delta theta. For example, taking this equation, we can see that the following. We can see that delta B, I'm sorry for everything, the information looks a little bit untidy. Delta B is equal to B tan theta equal to B tan theta delta theta. So this is the first one. The second one, if we just try to evaluate from this one, now here we have delta B, which is known in terms of delta theta and delta A. So just delta A is now a function in delta theta. Delta A is equal to delta B sine theta. As we already mentioned, delta B is B tan theta delta theta. So we will have sine squared theta 6. So we have delta A equal to, as we already mentioned, delta B. You have B sine squared theta. So let us write one more page now. Let us increase the number of pages. Let us copy the most important equations. Let us copy the important equations again. Delta B, we already wrote, yes, delta B is B tan theta delta theta. So this is the first one. Delta B is B tan theta delta theta. B tan theta, yes. So what about delta A? Delta A is equal to B cosine theta delta theta. Delta A plus another term, delta A B cosine theta delta theta plus delta B sine theta plus delta B sine theta. Now delta B sine theta, which is B tan theta sine theta. So this is delta B. B tan theta, yes, delta theta. So we have everything in terms of delta theta. B sine theta delta theta. Delta B, yes. Delta B is B tan theta delta theta multiply sine theta. It's okay. So we have delta A in terms of delta theta. So finally we need just delta D. Delta D is equal to minus delta A minus delta B. Delta D is equal to minus delta A minus delta B. That's all. So it can be written this way: minus B tan theta minus, of course, minus B cosine theta minus B tan theta sine theta, and you can take a common factor delta theta. That's all. So we are ready to return back to the equation of the virtual work, principle of virtual work, which is simply f delta d plus w delta a equal to 0. F delta d plus w delta a equal to 0. F delta d so this is delta d plus w delta a Of course, this is multiplied by delta theta. However, delta theta is arbitrary, and this is all equal to 0. So it is just the coefficient of delta theta that is equal to 0. Now, B itself, if you remember what is the definition of B, it was the tilted part of the rod. So this was B. So B itself is not a 0. So you can just take it outside. You can just cancel it out from the equation. So you can just cancel the B. You can just cancel B. So what we get now? If we cancel B, so we have the following. We have F multiply tan theta plus cosine theta plus tan theta sine theta is equal to W cosine theta plus tan theta sine theta. So this is what we get now. Because we can take the negative to the left hand side, so it will be a positive one. So we can try to simplify this further by writing or taking tan theta 1 plus sine theta. So we have the common factor plus cosine theta equal to W multiply cosine theta plus tan theta sine theta. So if you are interested in just getting the force over the value of F, so we need to divide here. So it will be F it will be equal to W cosine theta plus tan theta sine theta over tan theta one plus sine theta plus cosine theta also. So we can try to make the following simplification. Divide the numerator and the numerator by cosine theta plus tan theta sine theta, so we have a 1 plus what? Plus tan theta over cosine theta plus tan theta sine theta. So is it even possible to simplify this one further? So this sine is a sine over a cosine. This is a sine over a cosine. So let us go one page further now. F equal to W multiply 1 over, now let us see how to go 1 over 1 plus a very strange fraction. It's a tan theta over cosine theta. So let us write everything in terms of the freedom. Tan theta over cosine theta, tan theta over cosine theta plus tan theta over cosine theta plus tan theta sine theta. So what is this? It's W multiply 1 over 1, and this tan is sine over cosine. So if you multiply the numerator by cosine, you will have cosine squared theta plus sine squared theta, which is a 1. So simply we get the relation I was searching for, which is F equal W over 1 plus sine theta.